Hi guys, welcome to 314 part 1 where we look at polar function graphs. Now, polar graphs are a little bit different than what you may have seen before, but we're going to try and hopefully make the connection between what we've done with graphing just like sine of x with graphing what we call a polar curve, where we've talked about oops, I didn't mean to raise my hand, meant to share my screen, where we talked about like extrema and maxes and mins, and I know we talked about polar points as well. Okay, so let's look at this visually kind of first. So let's start with something that we know pretty well. Let's start with sine of x, okay? So this is my sine of x curve. If I graph this, you can see that it's going to look like a circle that goes up on the y-axis. If I graphed cosine of x, this looks like, well, it's already graphed it for you. It's a circle that goes right on the x-axis. What if I did negative cosine of x? That goes to the left. Think cosine x, sine y, and then negative sine x. We can also do this with more complicated functions, like maybe cosine of 2x. Okay, so if I have something like this, and notice that as I plot this, this is actually what we call a rose curve, where it has 4 petals here. We can also do maybe something like this. Okay, this is called a cardioid. And if I graph like this, it looks kind of like a heart, maybe a smushed heart a little bit. So this is really kind of the meat. This is kind of the more challenging stuff to think about because it's not as intuitive. So I'm going to try and go as slow as I possibly can. Okay. So that's what it looks like visually, and kind of the connection to, you can see this is 3 cosine of 3x has an amplitude of 3 and a midline of y equals 3 as well. Okay, I need to erase this because I already recorded this video and my screen sharing wasn't working. So actually 3 videos and I want to cry. But so ignore the fact that I'm going to erase what I already have here. I might leave in the points just to make your life easier, but guess you get lucky a little bit. All right, so if I have something like 4 sine of theta, I would take a second, pause it, try not to look at the answers on the screen. But I could take each value of theta, plug it into that, and then get the output. So for example, if I was doing pi over 6, 4 times sine of pi over 6, sine of pi over 6 is 1/2. 1/2 times 4 is 2. So if I go to plot these, remember if it's positive, you're saying go that many steps towards that angle. So 0, 0, 2 steps towards pi over 6, 4 steps towards pi over 2, 2 steps towards 5 pi over 6, and then 0. So it's going to be a circle that goes up to 4. On this one, negative 3 cosine of theta, maybe you remember from what I just said, that negative cosine is going to happen on the x-axis, and it's going to be going to the left because it's negative. So in part C, it says if a polar equation involves only r equals a sine theta and r equals a cosine theta, well, if r is positive, if it's sine of theta, it's going to be going up. If it's cosine, it's going to be going to the right. If r is negative, if it's sine, it's going to be going down. And if it's cosine, it's going to be going left. Hopefully that makes sense. Sine is what we talked about with y, cosine is x, all that fun stuff. All right, go ahead and flip the page. And we're going to talk about some other curves that you will see. All right. Again, sorry, I already have stuff here. Try to remember to erase this before the next one. So what we just talked about, what I showed you was a rose curve, okay? And how you identify rose curves is in the form A cosine of n times theta or A times sine of n times theta. The n is the value in front of the theta. Okay, here we go. All right, so in this case, okay, this part is important. It says if n is odd, there will be n petals. If n is even, you will have 2 n petals. So let's practice first just identifying n and how many petals there will be. So n is my number in front of theta, so this is 3. 3 is odd, so it will have 3 petals. N is 5. 5 is odd, so it will have 5 petals. In this one, n is the number in front of theta, n is 4. Well, it'll have 2 n petals, so that means it will have 8 petals. In this one, n is 2. That's even, so it will have 2 n petals. 2 times 2 gives me 4 petals. Now, we're also going to talk about in the next video the domain restrictions to graph a full cycle. So I'm just going to put this here for right now. You don't need to necessarily deal with it right this second, but you will in the next video. So one cycle for the rose curves means if n is odd, it's going to be from 0 to pi. And if n is even, it's going to be from 0 to 2 pi. And maybe you can remember if n is even, 2n petals, 2 pi. Maybe that connects. So remember, polar is only on multiple choice. So I'm not going to ask you to graph something like this by hand, but you should be able to recognize if this is a multiple choice question and I give you something like this, well, I'm looking for a rose curve that has 3 petals. You can also always plot a point or pick a point to plot. So if I picked 0, for example, that would give me 2 cosine of 0. Cosine of 0 is 1, so that means 2. So the point here would be r comma theta. Okay, so 2, 0. So I'm taking 2 steps towards the angle 0. So that means that that's going to be a point. So if this was multiple choice, you could kind of narrow down, okay, which one has that point. This will have x-axis symmetry, or sometimes you'll hear this referred to as polar axis symmetry because it's a cosine function. Okay. Let's look at one more. Let's look at 4 sine of 2 theta. This will have 4 petals. If we pick a point to plug in, if I pick 0 or pi over 2, it gets kind of boring because those are all just 0. So let's pick pi over 4. Well, 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1, so I have 4 times 1. So that means that at pi over 4, which is exactly in the middle, I should be out at 4. Again, we said we should have 4 petals. It's going to look something like this. Again, if you have your calculator, I'm going to show you how to graph this on your calculator as well. This is just kind of narrowing down my options if this was given to you without a calculator of how to be able to know what the graph would in general look like. Again, you're not going to have to graph it from scratch by hand. All right. And then we have cardioids and limacons. Okay, it's kind of a weird word to say. But that's always in the form a plus b cosine theta or a plus b or minus sine of theta. So the biggest tip I can give you with these is figure out which axis they'll be on, and that will really narrow down your options, okay? So for example, if it is a positive cosine, like this one, that's going to fall on the right, just like when we did 4 cosine theta or whatever that was. Negative sine will fall down on the y-axis. The maximum distance is always going to be that 2 plus 2. And if it's negative, you still just take the absolute value. So it's going to go out to 4, and it's going to look something like this. Okay, because a divided by b, a and b, 2 divided by 2 equals 1, that means it's going to be a cardioid. You're not going to have to name these, but it can help if you know the names to think about what these would look like. All right, this one goes down, we just said. So it's going to go down to negative 4. That's going to be the maximum distance because 2 plus 2. That's kind of a real heart. That shouldn't look that should look a little more smushed. But a divided by b also equals 1 when we take the absolute value, so that's why this is a cardioid as well. All right, this one's same idea on all of these, okay? This is a negative cosine, so that will go to the left. D is a positive sine, so that will go up. Now, on these, my ratio here, a divided by b, is less than 1, which means it's going to have an inner loop. So again, just recognizing what do I know that this should in general look like. You can always plug in a point to verify. The max distance will be 1 plus 2, meaning it will be 3 away. Okay, and it'll look, I'm very bad at drawing these, I'm going to warn you. something like that. Let me graph it on GeoGebra so you can see a little bit better. 1 minus 2 cosine x. And if I move my point, that's what it's going to look like. Okay, max distance goes out to -3, so 3 units away. All right, let's look at one more. Let's look at, well, actually, let's just in general look at this right quick. So this is positive cosine, so it should go to the right. Negative sine should go down. Fix that. All right, so in this case, my ratio is bigger than 1, so it's going to have kind of like a little bit of a dimple, and as that ratio gets bigger, it's going to look even more like a circle. So let me just show you these on GeoGebra so you can see, and maybe you want to sketch a picture of these in your notes as well. But 3 plus 2 cosine of x looks something like that. Still has that little dimple there. And then 5 minus 2 sine x, this one, zoom out, looks even more like a circle. So as that ratio gets bigger and bigger and bigger. So if you had 5 divided by 2, that's about, or it's not about, it's exactly 2.5. And then if you get bigger from there. Okay. So polar graphs, I'm going to maybe link this onto Canvas so you can kind of play around and see what happens. So for example, we said if that's even, that's going to be a rose curve with 2 end petals. Well, what if I change that to being odd? Then it's only going to have 3 petals. What if I tried 7? That will have 7 petals. What if I tried to do cosine of, or 2 cosine of x? And think about trying to predict what that will look like without actually typing it in. And then type it in and check. And you can see as you move this point along that it is tracing that curve using values of r and theta. So that wraps up the first part of 314 part 1, which deals with polar function graphs. We will look at graphing a full cycle. We'll look at typing it in your calculator in the next video, how to do that. There's something called polar mode, just like there's radian and degree mode. So we'll take a look at that as well as some intersections as well. Have a great rest of your day.